All right, so let's begin with a particle motion using technology warm-up. So the idea is that free response questions are going to be calculator, some are going to be non-calculator, and they're all going to incorporate different types of concepts and ideas that we studied over the course of this year. One of the major concepts that we've looked at is particle motion. So although today's warm-up really doesn't directly relate to today's lesson, I want to just start to continue to see free response questions and work through them. So it says a particle moves along a line. The time is 0 to 8. So that's really important because sometimes when you're giving your answers, you want to make sure that you don't go beyond the given time interval. We are told velocity, so that tells me that that's the first derivative. So you're going to be given velocity a lot because what they're going to have you do is work forwards and backwards off of that. They're going to have you integrate it so that you find position, and they want to make sure you know how to integrate it, and they want to make sure you know how to interpret the integration. And then you can also have to derive it. So they're going to give you velocity a lot. This right here is our initial condition. They're giving me that so that I can apply the fundamental theorem of calculus at some point in this problem. So I have an initial condition. I have a rate or a derivative. And then we're going to interpret the first question. Find all of the values of t in the interval from 4 to 7, so they even restricted my interval more, for which the speed, so immediately I'm thinking absolute value, of the particle is 5. So, calculator question. If the speed of the particle is 5, then my y equals, I'm putting in a 5. That's the first thought I have. Next, I'm putting in the absolute value of velocity because I need to find all the values in which the speed is 5. So I'm looking for the absolute value of velocity to equal 5. So I'm looking for points of intersection. So go over to math, go to absolute value. Velocity is x minus 3 natural log x plus 2 plus 2x sine alpha y equals, get my fraction bar, x squared all over 12. Just going to make sure everything is good. I'm going to put in my parentheses here to close off my sign. I'm going to go back and make sure I have all the right positives and negatives and things multiplied together. I'm going to go to my window. I have no idea what's happening on the y values, but I know in terms of the x values, I'm looking for intersections at 4 and 7. So you could either start it at 4 and 7. If you like to see a little bit before, you could put in 3.8 and maybe 7.5 just to give you an idea of what's happening right before or right after. So we're going to graph it. So we know 5's right there in the middle. Now we're looking for all the points in which it's going to hit 5. So you go second, trace, go to intersect. So I believe if I go all the way over here, I'm going to think that first point's out of my range. It is. See how it's at 3.6? So I want to ignore that first one we're seeing on the graph. I'm going to go all the way over to the right, and we're going to go to this point right here. I'm going to hit enter 3 times near that point, and then I'm going to write down my t value. So it's t equals 5.621. So I have my 3 decimals. I'm going to go over to second trace, go to intersect, and I'm going to go over to that second point, enter 3 times, and I see that they intersect at 6.52. And I do have my calculator set to 3 decimals. So if you have yours set to more, you might not have had that same rounding. Okay, so we have t equals 5.621 and t equals 6.520. Now, this is speed, and we were told that this is velocity. And I was just going through to see if we were given any units. We were not. Write an expression involving an integral that gives the position s of t. Use this expression to find the position of the particle at time t equals 3. So, if I want to write an expression involving an integral, this is the fundamental theorem of calculus, or you could take into account lesson 7-1, which was net change. So final position is s of t. It's equal to initial position, which is s of 0, plus the integral from 0 to t of v of t dt. So this is what we call the general form. For this problem, we're trying to find the position of the particle at time t equals 3. So where I have my t here, I'm going to change that to 3. So we'd have s of t, and we change that t to a 3. So it'd be s of 3 equals s of 0 plus the integral from 0 to 3 of v of t dt. So general, specific, and then to find that, you could just go again back to your calculator. Now, if you recall, we could delete the absolute values out of my function in y2, and then I could use that when I do my problem over here. So I'm going to leave this. S of 0 is negative 3 according to the initial condition, so it's negative 3 plus whatever that integral value is. So I'm going to go to math 9. I'm going to go 0 to 3. I'm going to hit vars, y vars function y2. This is in terms of x's. And I'm going to get my answer. And I get negative 3.263. So if you subtract 3 from that, we get that the position of the particle at 3 seconds is negative 6.263. Part C, find all times in the interval from 0 to 8 at which the particle changes direction. So the particle changes direction when the sign of velocity changes. So again, particle changes direction when sign of velocity changes. So we already have velocity in our calculator. I'm going to delete that 5 out of y1. I'm going to change my window back to 0 and 8. And I'm going to hit graph and just see what I get. So velocity starts in the negatives. It hits 0 right here. It goes up to the positives. Velocity is coming back down. It hits 0 again and becomes negative. So the velocity graph has 2 sign changes, a sign change over here and a sign change over there. So that tells me that there are 2 times the particle changes direction. So it says find all times in the interval at which the particle changes direction, justify your answer. So I'm going to go to second trace. I'm going to go to 0, because when the velocity is 0 is where it changes direction. So I'm going to go to the left of that 0, I'm going to go to the right of that 0, and I'm going to find that 0. So the first 0, or time, is at 2.341. And then I'm going to do it again. I'm going to find the next 0. So I'm going to go over, 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 over. Enter, enter, enter. And I get the time of the second 0 is 6.127. So my justification, and this is where you have to be very particular, this would earn you 1 point. The second point is earned in your justification. So I would say the particle changes direction when v of t equals 0 and changes sign. At t equals 2.341, v of t is less than 0 when t is less than 2.341, and v of t is greater than 0 when t is greater than 2.341. Therefore, changes direction. Now that might be a little overkill. This particular sentence here kind of covers exactly what you're trying to say. If you really wanted to put it into words, this is an alternative definition where you actually tell them that it's negative and then it's positive. You could also have used your words and said that. So, make sure they know when you're justifying that you know it occurs at a 0 and a sign change. Then it says, is the speed of the particle increasing or decreasing at 7? So speed is where velocity and acceleration either have the same sign or opposing signs. So we're going to look at v of 7 to start. And again, velocity is in your y equals. So you could go over to your table and you could just type in 7. And v of 7 is negative 10.91. So I'd say v of 7 equals negative 10.91. And then I'm going to find a of 7. So again, it's in my function. So I could go to my home screen, hit math 8 this time. So I find the derivative of the function. And I'm finding the derivative of that function at 7. And I see that the acceleration at 7 is negative 10.561. So my justification is that the speed of the particle is increasing because at time t equals 7, v of 7 and a of 7 are both negative. Yep. So like up here, you want to make it x and x. I mean, it wouldn't change. Yeah, it doesn't really change anything. As long as your variables are consistent, then you're okay. So like that's why like if you do have y's and x's, you have to keep them on the same side. Or if like we change something to a u, you can't leave behind an x. So yeah, if you wrote v of x and d of x, they wouldn't dock you. But if you have v of x and d of x, then you better have an x here. Yeah. Right. But when you integrate this, which I would never want to integrate that velocity by hand, technically the variable in here is t. So like, let me give you a different example. Like, so if you had s of t equals s of 0 minus the integral of 0 to t, and let's just put in an easy function. Like, let's say this is t squared minus t dt. So that's your general. So final, initial, and then we can find whatever final position we want. Then this would become, if I wanted to find the final position at 4 seconds, it's s of 4 equals s of 0 minus the integral from 0 to 4. And then it just sort of like tags along. So you have s of 4 equals s of 0, and we'll keep it that -3, whole minus, find the antiderivative of your t's. So it'd be 1/3 t cubed minus 1/2 t squared. And then you're plugging in a t value of 4 and a t value of 0. So as I said, like changing it to x's doesn't change anything. But it's like, it goes back to that fundamental theorem of calc, where like if you even think back to that, like it went 0 to x and sometimes these were t values, but then like once you found your antiderivative, it didn't matter because then you ended up replacing those t's back with that x. Okay. You're very welcome. All right. Today's the day. It's your final new calc lesson. We're on 7-3. And it's like the culminating lesson of all lessons. We're going to take and we're going to put together everything you've ever known about mathematics. Because we're going back to geometry with area. We're going to have a whole lot of algebra. And, we're throwing in integrals. So we're shifting away from that definite integral and one dimensionality, and we're moving into a two-dimensional world. So think of amphitheaters, you're thinking of cylinders. So like this amphitheater over here in Kansas City is like one of the best ones to look at because you can see in that drawing how I have a series of semicircles where all of their widths are the same, but their heights are different. So the object is getting taller, and you can almost see like a quadratic formula here in terms of the shape of it. And if you wanted to find the area and volume that that building took up, then you would break it into all of these like mini cross sections. And essentially that's what we're doing today. If we want to find the volume of an object that we can't necessarily find the volume of without breaking it into cross sections, then that's how we're going to look at this. We're going to look at all of these mini little kind of Riemann sum concepts again. So we have volume of cross sections, and we're going to take our volume in two ways. Just like we had the area between two curves, and sometimes we looked at it with respect to x, and sometimes we looked at it with respect to y. In terms of volumes, sometimes we're going to look at it with respect to x, and sometimes we're going to look at it with respect to y. And anytime we change direction, it's important to know that this is taken with a perpendicular piece to the axis. So what that means is that if you are looking at the volume with respect to x, then it's going to be perpendicular to the x-axis. So here is our radius. Our radius is perpendicular to the x-axis. If I were going to use this aspect here, then my radius would be perpendicular to my y-axis. And the rotation would be with respect to the x-axis. So it's a little bit different looking depending on how you talk about it. So I told you that today is that culminating day where we got to go back to our geometry analysis. So we got to talk about, in geometry, all of our geometric shapes and all of their important formulas. So if we had a square, then you need to know the length of a side. So if we have a square, we need to know length of side. And that should make sense. If we know the length of the side, then we can find the area of the square. So the area of a square is s squared. So length of a side, where s represents the length of the side. If you want to know a rectangle's area, then you need to know the length of two sides. And we always learned or denoted those as a length and width. So the area of a rectangle is L times W. If you want to find the area of a circle, then you need its radius. If you want to find the area of a semicircle, you still need its radius. Now you could take into account being given a diameter, because a radius is just half the diameter. So if you're given diameter, then you're still pretty much given radius. And the semicircle is half of a circle. So area of a circle is pi r squared. So area of a semicircle is 1/2 pi r squared. And then if you want to know the area of a triangle, then you need the length of its base, B, and height. Area of a triangle is 1/2 base times height. So pretty much when it comes to finding volumes with cross sections, these are the four shapes we're going to use, which means these are the four formulas we are going to integrate. Because again, if you take the derivative of volume, you get area. If you integrate area, then you get volume. So let's jump right into it. Example number 1, a triangular based volume. So we have the function f of x equals 1 minus x over 2. We have the function g of x equals -1 plus x over 2. And we know x of 0. I'm going to draw my graphs so that I can see where these triangles are made. So the first graph has a y-intercept of 1 and a slope of -1/2. So it's going down 1 over 2. My second graph has a y-intercept of -1 and a positive slope of 1/2. And again, we are told that we want to find the volume of a solid in which the base of its region is bounded by f of x, g of x, and x equals 0. So the line x equals 0 is vertical. So we are trying to find the volume here. So if yesterday's lesson was what we were doing, then you would find the area between the two curves, and you would have integrated the top curve, which was f of x, minus the bottom curve, which was g of x, and you would have bounded it from 0 to 2. What we're going to do today is, instead of finding top minus bottom with those bounds, we're going to find base and height to find areas of all these tiny little rectangles. Because technically, and I have like a little video to sort of show you, because I'm not very good at drawing, what we're looking at. So I want to go over to sharing my screen. We're going to go to a video. So this video would be the volume of a cross section that is rectangular. But again, you can kind of see the triangular region here. So I'm just going to let you watch how they draw their cross sections. So the idea is that here is our x-axis, here's our y-axis. Now we also have this third axis C, so that if our graph was here and we wanted to find its volume, technically you're adding all of these rectangular regions above it, and you're finding the volume. So this would be a volume of a cross section with a rectangle. The first one we're looking at here is a triangle. So in order to do that rectangle, dx is going to represent the width of the rectangle, and dy is going to be represented, y is going to represent your length, and x is going to represent the height. So you end up with volume, which is length times width times height, utilizing all three pieces, where y, the y equation given to you, is the length, the height is h, and then dx is the width. I don't think he draws. So here is the other three-dimensional view. So this is looking at it from the side. That's like this piece over here. So you can see how all of the y values are changing like they did with our Riemann sum. You can see how dx is just like the width of the rectangle from our Riemann sum. And then the height is given somehow. Well, the height is given from our volume equation that we've created. So think about height, or base and area of a triangle. Height is half the base. So there's all my bases. So here's a semicircle. So here's your first curve, here's your second curve. You can see how the curves between them give you diameter. And then we talked about how radius is half the diameter. And let's go back to our example with a triangle and talk about the same idea. So essentially what's happening is, here's your triangle. It's essentially creating triangles, which I told you can't draw. Many, 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 many triangles on top of that. So it says the cross sections are perpendicular to the x-axis. So here's my x-axis. That's why my triangles are like coming up and out of the page. And this time we want to make them squares. So in order to make a side length of a square, we're going to say S is equal to, so if these now became squares, the base, or the length of the square, is going to be the distance between the top curve and the bottom curve. So the length of the square, or the side of the square, would be the top curve minus the bottom curve. So, to find the volume of a solid with bases that are squares, volume is going to equal the integral of the area. It's from 0 to 2 because that's where the two functions intersect. And this is the length, or the side of a square. So area integrated gives you volume. So you're going to integrate the side, 2 minus x squared. So volume equals the integral of the area. Area in this case is s squared. S is 2 minus x. And we begin at 0 and end at 2 because it was bounded by the x-axis and the point of intersection. I'm going to FOIL this. You could also do U substitution. Personally, I'm better at FOILing and integrating a quadratic than I would want to do U sub. So I'm going to say my volume integral is equal to 4 minus, so this would double duplicate, so it'd be negative 2x, so it's negative 4x. A negative times a negative would give you a positive x squared. And then my antiderivative would be 4x minus 4x squared over 2, so that's 2x squared plus 1/3 x cubed. And I'm evaluating from 2 to 0. What's nice about this is that the zeros, or the second half, is all going to go away. So I'm going to plug in my 2. 4 times 2 is 8. 2 squared is 4. 4 times 2 is 8. 2 cubed is 8. So 8 minus 8 cancels, and the volume of that cross section with square bases is 8/3. Now it says the volume of a cross section with semicircles. So you have that same triangle graph, but now coming up are circles. And again, it would make sense as a semicircle because we're not going down below. So if you think about a semicircle, here's its top, there's the radius. So the radius is going to be represented by that height. The radius of a circle is also equally out to the side. So the radius could go that way, it could go this way, etc. So the radius is going to be half the length of that whole side. So we already said that that side length was the difference from f minus g. So the radius is going to be half of f of x minus g of x. So it's going to be half of 2 minus x. So the volume is going to equal 0 to 2. And now it's the semicircle. So area of a semicircle is 1/2 pi r squared. So r is 1/2 2 minus x squared. If you recall our rules, 1/2 and pi is a constant, so it can come out in front of my equation. And then in here, that squared is kind of distributing to all of this. Personally, I would maybe distribute that 1/2 in, just to sort of make my life a little easier. You could also conversely take it out. So you could square that 1/2, or you could distribute it in. Either way. If I take it out, then I don't have to worry about fractions. So what I would do is think of it like this, 0 to 2. I'm going to distribute that so you get 1/4, 2 minus x squared dx. And then the reason I'm going to take this out, especially if I already did this problem up here, is this now becomes pi/8 from 0 to 2 of 2 minus x squared dx. But what do I already know about 0 to 2 of 2 minus x squared? I already did that. So by taking out that 1/4, I can now say that this is pi/8 times 8/3. And the volume of this semicircles is pi/3, because I can simply substitute in my answer from part A. The cross sections are now rectangles. And since they're rectangles, the base and the height wouldn't be the same. So you have your triangular base, but now since these are rectangles, here's the base of your rectangle. The height's going to be changing. So they just kind of gave you a flat out, oh, the height is 3. So your base would still be that f minus g, which we already know is 2 minus x. So if you go volume of a rectangle, it's 0 to 2. It's base times height, or length times width. So that would be the length, which is f minus g, which is 2 minus x, times a height, which is 3, dx. So area of the rectangle is 2 minus x times 3 dx. You got two choices. You can distribute that in. So you'd have 0 to 2 of 6 minus 3x dx. So then that becomes 6x minus 3x squared over 2, evaluating from 2 to 0. So you get 12 minus 2 squared is 4. 4 divided by 2 is 2. 2 times 3, negative 6. And then 0, 0. So the volume of the cross section with rectangular cross sections is 6. So again, you have a whole bunch of rectangles going down. And what's happening, each rectangle is getting a little bit smaller until you get to that end. What if they're equilateral triangles? So if you think about this graph again, and now you're drawing a triangle up in the air. An equilateral triangle means all of my angles are 60. An equilateral triangle would then have a face that looks like this. So here's F, here's G. So this line is F, this line is G. That's your point 2, 0. So what that means is that, well, sorry, not your point 2, 0, because now I want you to look at, like, we're essentially looking at this triangle here. So if I drew my triangle straight up in the air, here's my height, here's my F and G, like in these corners. So here's your triangle going out in the air. This would be 60, this is 60, and this is 60 because it's an equilateral triangle. But if that top is 60, then the height cuts that angle in half. So this is a 30 degree if you only talk about this. So this becomes a 30, 60, and 90 triangle. And the base of the triangle is that 2 minus x, because it's f minus g, because it's hitting at these two corners right here. What I don't know is the height, and in order to find the area of a triangle, I need the height of the triangle. So we got to go back to our days of Pythagorean theorem and talk about the general height of a 30, 60, 90 triangle. So if the entire base is 2 minus x, then if we just look at that 30, 60, 90, so here's my 60, here's my 30, here's my 90, this is 2 minus x divided by 2. And if I want to find this side right here that represents my height, then you could say, well, you have two choices. You could have had your 30, 60, 90 triangles memorized. So if you go back to a 30, 60, 90 triangle, let me pull one up. Back in the day, we used to have these two triangles here. So we used to talk about, there we go. No, so I just wanted that picture big. There we go. So we had our two triangles. We had our 45, 45, 90, and we had our 30, 60, 90. So here's my 30, here's my 60. This is my x. So the height was x square roots of 3. So we're going to use equilateral triangles a lot. So that 30, 60, 90 is going to come into play a lot. So knowing height is x root 3, it really saves you from having to go back and do Pythagorean theorem or do SOHCAHTOA and all of that messiness. So just kind of like make a mental note of this because we're going to be using it for our homework today. So that takes you back to our y value. I didn't want it to be confusing. So if this is x, then my height, so the length of base, would be equal to 2 minus x. The height would be equal to 2 minus x over 2 times root 3. And that should seem semi-familiar to you because if you think about the sine and cosine of like 30 and 60 degrees, both of them incorporate a root 3 over 2. And you can actually see that within this problem right here. So the volume of a triangle cross-section is going to be that 0 to 2, 1/2 base, which is 2 minus x, and height, which is 2 minus x over 2 root 3. I automatically wrote the 1/2 out in front because you know you can pull out a constant. You can actually take out this constant of root 3, and we can take out the constant 2. And hopefully that looks familiar to you because that's 2 minus x squared, which we've already integrated way back again in part A. So this becomes root 3 over 4 times 8 thirds. 8 and 4 become 2, so you get 2 square roots of 3. Over 3. Questions, comments, concerns? Is everybody okay with that? That is our, big idea. We're going to do a whole nother second example, but I want to make sure before I move on, we can kind of see those volumes of cross sections. You see where it's coming from and you understand how these are representing volumes by integrating area. So all we're going to do now is change the equation. Part A, B, C, and D, all of that stays the same. What's now changing is what we're taking the base with respect to. So it says find the volume of a solid in which the base is a circle. So last base was a triangle with origin as its center. So it's centered here. And its radius is 2. So that means it goes out 2, up 2, out 2, down 2. If you think about the area of a circle equation or the equation of a circle in general, it's x squared plus y squared equals r squared. So if my radius is 2, then my equation is x squared plus y squared equals r squared. So we're going to rewrite that so it's y equals. So it's y equals plus or minus the square root of 4 minus x squared. Because you subtract over your x squared and then take the square root. And when you take the square root, you need the plus or minus because the positive would represent the top half and the minus would represent the bottom half. So that means that this right here is the positive square root and this right here is the negative square root. And the reason I care about that, is because you have to know which one's top and which one's bottom when you find your base of a cross section. So it says the cross sections perpendicular to the x-axis are squares. So again, now we're coming up and creating a square. So the area of a square is base times height, where they're the same. So your base is that top minus the bottom. That minus the minus is nice because essentially it turns to a positive. So your base is 2, 4 minus x squared. So the volume this time, it starts here and goes to there. So my integral is going to be negative 2 to 2. That constant can come out in front. And it's square root 4 minus x squared, because it's s and it's s squared. So what's nice is the square and the square root cancel. And now we're just taking the integral of a quadratic. What makes these ones a little worse is because now it doesn't start at 0, it starts at negative 2, so you got to plug in negative 2 also. So I have 8 minus 8/3. That negative in front's going to distribute, so that becomes a positive 8. This was already positive, so it becomes negative. So I have 8 plus 8, which is 16.